The acid ionization constant, or Ka, is the equilibrium expression for an acid. And so the Ka is listed in your data booklet, and it is a representation of the acid in water making hydronium. So for this equation, we've got a weak acid, hydrofluoric acid, reacting with water to make hydronium and fluoride. This is my acid, this is my conjugate, or this is my Bronsted-Lowry acid, this is the Bronsted-Lowry base. The acid in the reactants has the conjugate base, and the water has a conjugate acid in the products. This reaction will be less than 50% forward reaction. It's a weak acid, and we could consult the data booklet to spot that. But for this equation, we're going to have the concentration of hydronium in mole per liter and the concentration of fluoride in mole per liter divided by the concentration of the acid at equilibrium. So this is the equilibrium constant for an acid ionization, or the Ka. 6 strong acids have extremely large Kas. All other acids have lower Kas. And so when we're looking in the data booklet, we're going to see that the 6 strong acids here are all listed with very large Kas. That's because the equilibrium is quantitative, and so it's approaching 0% or almost none of the acid is actually that molecule at equilibrium. Almost all of it has become hydronium and the acid. So water is here, and with these, it strongly favors the reactants, or the products. But for a weak acid here, you can see that this is going to be less than 50% forward reaction. Now the Kas are listed in the data booklet, and we can read them off and we will use them, but they're experimentally determined by looking at the equilibrium concentrations of each of the chemicals. Now, we can do an ICE table to calculate the Ka for a chemical. So in this example, it says the pH of a 1.0 mole per liter solution of acetic acid is carefully measured to be 2.38. And so if we did an ICE table for this, we've got our acetic acid. I don't include water because it's the pure liquid form. I've got hydronium, and I've got acetate. And there are a few nice things with equilibrium tables with acids. And one of them is that the coefficient for these are always going to be 1. Even if it's a polyprotic acid that's got more than one hydrogen to give up, we only look at one hydrogen going at a time. So my initial concentration of the acid is 1.00 mole per liter. We have 0 amount of that, but at equilibrium, the pH equals 2.38. So the concentration of hydronium at equilibrium is 10 to the negative pH. That's how I calculate the concentration of an acid. So if I put that into my calculator, I am going to get 4.2 times 10 to the negative 3 mole per liter. So that's going to be 0.0042 mole per liter. So 0.0042 is being made. This is in a 1-to-1 ratio, so this is going to be making it at the same rate. The change for the acid, we're going to subtract now because we're using that amount of acid up, is minus 0.0042 mole per liter times 1 over 1, and so it's minus 0.0042 mole per liter. And so if I put that into my calculator, so I take 1 minus that, I'm going to get 0.99583 is the number that would go in here. But I can't have fewer sig digs than that, so I have to round it off to 2 decimal places. And so this is actually 1.00 because this is greater than 4, and so I round it up. So really the change has been so small that it's actually not measurable. So here I'm going to calculate my Ka equals the equilibrium concentration of hydronium times the anion. So that's the conjugate base, and then divided by the acid, so CH3COOH. And my Ka will equal 0.0042 mole per liter times 0.0042 mole per liter divided by 1.00 mole per liter. And this is going to give me my Ka. And I end up getting a Ka of 1.8 times 10 to the negative 5. And it doesn't get units because it's an equilibrium constant. So by using an ICE table, I can directly calculate the Ka for a question. We'll do another example here. So if you want to, maybe pause and try doing this question. And I'll begin in a second. So I need an ICE table. They want me to calculate a Ka. Here's my initial concentration, and here's my acid concentration. So I've got sulfurous acid, and I've got hydroniums. I've got hydrogen sulfite, and my initial here is 0.400 mole per liter. This is 0. My change in equilibrium. So I calculate the concentration of hydronium, which incidentally will be the same as the hydrogen sulfite because it's a 1-to-1 ratio. So I'm going to calculate that with 10 to the negative pH. That's 10 to the negative 1.17. And I end up getting 0.0676 mole per liter. Now I do want to draw your attention to this. This pH has only 2 sig digs. You'll remember that for pH or pOH, you start counting significant digits after the decimal. So there are only 2 sig digs in that value, and so I should only have 2 sig digs in this number as well. So this should be 0.068. So I'm going to get 0.068 mole per liter, 0.068 mole per liter, because it's a 1-to-1 ratio. I get sometimes a little bit lazy in the acid. Oh, sorry. I got real lazy in that one because I did it wrong. It's 0.068. I get a little lazy sometimes with my coefficients here because with acids, it will always be a 1-to-1 ratio. So this is going to be minus 0.0068. And now if I take my 0.400 minus 0.068 and I round it to the 3 decimal places here, I'm going to get 0.332. And so in this case, the change was big enough to affect the equilibrium concentration of the acid. So when I'm calculating the Ka this time, it'll be 0.06. Oh, here, I'll write the equation because that's not a bad thing to do. We got the hydroniums times the 8 hydrogen sulfites over the concentration at equilibrium of hydrogen or of sulfurous acid. So 0.068 mole per liter times 0.068 mole per liter over 0.332 mole per liter, and we'll get our Ka. So we're getting a Ka of 1.4 times 10 to the negative 2. And we don't get any units for that because that's the Ka. So that's using experimental evidence to find it. Try doing questions 5 and 6, and you'll find those questions on page 743. So answers for these two questions are included in the textbook.